Go ahead and start the actual recording here. Okay, hello everyone, and welcome to the Thanksgiving Day stream of Handmade Hero. I am feeling a little bit better today, I'm pleased to report. I'm hoping that I am actually starting to recover from my illness. Not entirely yet, that's true, but we're getting a little better. So I'm hoping that maybe pretty soon here I will actually be able to stream to you completely illness-free, maybe next week, who knows. Anyway, we are going to be doing our finishing up our sound programming today, just taking a look at the sound output code that we made and basically trying to go in there and inspect it and make sure that we don't have bugs in there. So the sound output code is kind of finicky. Direct sound's a bit finicky, the way that you actually have to use it, and so we want to kind of go through that and just shore it up, make sure that everything is working properly. And then after that, if we get done with that, we'll be looking at timers. So if you're following along today and you've pre-ordered the source, pre-ordered the game and want to follow along with the source code, you're going to want to go and get the 007 zip. That is yesterday's source code, and you can follow along with us on the stream by using that source code here on day 8. Okay, so basically we're just going to jump right back to where we were yesterday. I've got a couple of cleanup things I wanted to talk about that don't have anything to do with audio, but we'll get to them later if we get to them. They're kind of on my notebook of just things to talk about that I didn't get to yesterday when I was talking about, because we went right up to the end with sound. So, here we go. Here we go. Basically, yesterday what we did is we learned how to basically lock our direct sound buffer, which basically asks direct sound to allow us to write into it, to update the contents of the sound that's being outputted by the sound card. And then what we did is we wrote a square wave into it, and then we told direct sound to unlock that, basically saying we're done writing into it, you can continue playing now. Now the other thing we did right at the end of the stream in the Q&A, people were asking why there was a pause. We waited until we had actually filled the buffer once in order to play the sound. So that's why this thing down here was true, because before we were starting it, before we had actually filled it at all, which causes a delay and so on. And so basically what we were doing is make sure we had it filled, then we start kicking it off, and we go from there. So the thing that I want to do today, first of all, is a square wave is a rather harsh wave. And so it's a little bit harder to hear if there are bugs in the sound output. And one of the things, I'll tell you a little story here on the Thanksgiving stream. We are not particularly time constrained today, by the way, so we could go a little long if we wanted to. I'll try not to, but we could. So one of the things that's actually kind of weird about audio, and that you kind of have to you just have to take it on faith when I tell you this. If you haven't had this experience yourself, then it may sound a little hard to believe, but you're just going to have to trust me it's true, and I'll tell you a story. So a long time ago, I don't know how many years it was now, probably 8 years, something like this, quite some time ago, we used to do a thing called the Indie Game Jam. And the Indie Game Jam was actually the very first game jam that ever existed. It was a thing that a bunch of us started. The very first one was held, Chris Hecker and Sean Barrett actually organized it out of a barn in Oakland, California. And basically it was a long time ago, and a bunch of us were sort of emailing about how computers had just gotten fast enough to maybe, if we tried, they could maybe render I think it was 10,000 or was it 100,000? It was either 10,000 or 100,000 sprites on the screen. Just sprites, like old school sprites. And so what we were talking about is, well, what kind of games could you make with 100,000 guys? And so out of that was born the idea of, why don't we just get all the game developers that we know, all of kind of the friendly game developers, who were all kind of professional. Everyone was working on AAA games at that time. There was no such thing as an indie scene. I don't know when this was, 2000, 99, something like this. Probably 2000 or 2001, I would say. So basically, we got everyone together and we said, all right, let's see if everyone comes down for a long weekend, how many games we could make that just play with the idea of having 100,000 guys. And so I worked on the engine for that jam. I think I did like a couple things, like the camera code and the loader that loaded Doom WAD files. That's where we got the sprites from. And then like Sean Barrett did like the renderer for it and stuff. that would actually try to push 100,000 guys at once and so on. And so that when everyone got there was basically this code that could go ahead and actually render 100,000 guys, and people could sort of make games with it. And that was the very first game jam that there ever was. And since then, there's been lots of that idea of having a game jam where everyone just kind of packs in and makes a bunch of games has kind of caught on. And there's been lots of game jams, but that was the first one I think that ever actually existed, a concept of a game jam. But anyway, a couple of years down the road, we had done multiple of these game jams, and we got to a particular one, in fact, the last one that was ever held, I believe it was the last one, I think it's the last one that was ever held, was an audio game jam. And the idea was games that use audio to basically to capture the gameplay. So the gameplay was going to be audio oriented. And the guy who was doing the engine for that one, because again, the pattern for the game jams following that first one was always we built an engine beforehand, so that's not part of the jam, so that everyone when they show up already has a code base and they're just writing the game piece on top of that, basically. So so people would volunteer to kind of work on the engine and that sort of stuff. So basically what happened is the person who was going to write the engine for that one was actually Ottman Binstock, who you may know now. He's like the chief architect at Oculus Rift. He used to work for Valve, and then he left to go do Oculus stuff at Oculus to do the 3D headsets. Anyway, he was writing the sound engine, and he was living in Japan at the time. And I had never been to Japan, and I had always wanted to go. So I went out to visit him shortly before the Indie Game Jam was supposed to be held. And so he was showing me at a cafe in Japan. I don't know what's going on because I can't really speak Japanese and all this stuff. I think it's awesome. I love Japan. It was like probably one of my favorite trips, if not my favorite trip of all time, going to Japan. So we're in a cafe in Japan, and basically we sit down, and of course, since we're in a cafe, the only way to listen to sound is on the headphones, right? That are plugged into Ottman's laptop, and he was just like showing me the engine. He's like, here's the stuff I built for the audio engine, got this, got that. And he has some pair of headphones that are like the standard $30 headphones, just random headphones that you might buy or that come with an iPod or something like that, an iPhone. And I've got actually, quite some time before, I had actually spent quite a bit of money. I had bought some professional grade headphones. When I was working on sound quite some time ago, I had actually asked some friends. I think it might have been John Blow who first recommended them to me. He basically said, they're called Etymotics. They're a headphone company. They make these headphones or whatever. They're really, really good, but they're expensive. So I bought some and I had them. And they are really great. They're amazing headphones. I've had the same pair for like a decade now. And so he's like showing this to me, and he's like, okay, listen to this. And I plug my headphones into his, laptop jack. And I listen to it, and I go, Ottman, you've got a bug. Like you're not quite aligned right on the buffer or something. You've got a bug. I can hear it. I can hear there's a little click there. And he plugs his in because he's got his headphones, and we unplug mine and he plugs his. He's like, I don't know what you're talking about. This sounds right. So I'm like, okay, here you go. And I give him my headphones. He puts them in. He puts the thing into the jack. He listens for a couple seconds and goes, I got to get a better set of headphones. The moral of this story is you would be surprised at exactly how much variance there is in the sound that comes out of both speakers and headphones when you plug them in. There are different kinds of effects that happen to the sound on the way out. When you plug in crappy headphones, crappy speakers, or even good speakers that are going through a system designed to make sound better or smoother or warmer or whatever you want to call it, there's a bunch of essentially filtering, there's a bunch of mutation to the sound that happens. And that mutation, while it may make the sound better, or it may make the sound worse, who knows, obscures the truth of what is actually getting put out of the line, put out the line by the computer. So if you have very subtle bugs that result in very subtle artifacts in the sound, it's entirely possible that your sound setup may not even allow you to hear them. That is how finicky this sort of stuff is. Small errors in how you fill the sound buffer, small gaps, small differences can produce frequencies that you can actually hear on, and artifacts you can actually hear on very, very good frequency response audio output, like headphones, speakers, whatever, but that you actually can't hear on lower quality or smoothing stuff that sort of munges with the sound. And so one thing that's definitely true is that if you really, really want to know if you've got a sound bug, beyond being able to inspect the code and try to verify things as much as you can, but if you really want to debug sound code, strangely enough, you kind of got to invest in a pair of headphones that have really, really good, accurate frequency response, that really accurately reproduce sound, because you may miss the bugs entirely. Anyway, Ottman did fix the bug, so it was gone by the time of the jam, but only because of the Etymotic headphones, so you got to give them props for putting out a good product, I guess. Anyway, that's a little story for you at the beginning of this stream. Hope you all enjoyed it. I'm not much of a storyteller, so I'm sure it could have been done in a more exciting way, possibly with visuals, but what can I say? All right, so I'm going to go ahead and open up Emacs here, just so we have our source code at hand in the editor as well. And then I'm basically going to take a second to talk about and think about how I want to go about verifying that this code works. So we've got a lot of moving parts here. There's a lot of things that we have to think about. First of all, when we come through it the first time, we fill the entire buffer, basically to give it something to play. And then we're going to go ahead and kick that off. So that means as soon as we fill the buffer the first time through this, then we kick off the playing here. It starts playing the sound, which means that play cursor, the thing that we're chasing essentially, is going to start moving through the buffer. It's going to start moving through the buffer, and direct sound is going to be playing what's in that buffer as the play cursor moves. And basically our job then, because we filled the entire buffer, so basically our right position is back to 0, our job is basically to go look at where that play cursor went to, and then go ahead and fill up to there. Now there's some complexities in how we do this, obviously, and there's some things that I want to point out that maybe aren't quite right. I'll give you an example of something that we're doing here that may be wrong. And so maybe we start to clean this code up, we start to think about these cases, start to debug it and make sure what's going on. But like, it was kind of a little hacky, it's test code and that's fine, but we're trying to actually pull this out into something we're going to use. Eventually we got to start thinking about these things. So one of the things that we're doing, for example, is we get the play cursor here. We take a look if the play cursor is equal to the byte to lock. We assume that we're basically starting out, everything's at 0, and we're just going to fill. Now, why might that be wrong, right? Well, one reason it might be wrong is because the byte to lock and the play cursor, well, we know what byte to lock will be after we're done. If we write the whole secondary buffer size, then byte to lock is basically going to be back at 0, right? Because it's going to advance one whole buffer size worth, but we're modding by the buffer size. So every time we advance it one whole buffer size, it's back to the exact same position it was where it started, which in this case would be 0. So if the play cursor has not moved, the next time we get back through this loop, if the play cursor is back where it was, we would refill the whole buffer again, which is totally wrong because the buffer hasn't actually been played. Does that make sense? And that could very legitimately happen depending on the system, because let's say that we are on a system whose play cursor reporting isn't particularly accurate. You have to remember the play cursor is basically an estimate of where the sound card is in terms of playing out the sound on the speakers in some sense, but we don't actually know how that's being computed. That has a lot to do with what the sound output chip is on your actual computer, what the drivers are doing, how frequently they update with direct sound, how direct sound and the kernel mixer decide how they're going to report those values, when they're going to report those values, when they're going to service those values. We have no idea what's going on here. And certainly in the old days, that play cursor used to actually be updated very infrequently, in fact. Nowadays, I suspect it's probably a lot more frequent, the updates that are coming through it, but it's worth remembering that it could actually happen, that doesn't actually advance. So that's kind of a bug waiting to happen, in my opinion. So this, we need a more accurate check than byte to lock equals play cursor. basically what we kind of want to do is maybe write something that's a little more intelligent and wants to see that play cursor advance a bit and know that it has actually been updated before we actually fill it again. Like one thing we could do trivially perhaps to increase the reliability of this code would be to check to make sure that in 2 times through the loop we have seen a different play cursor. Like don't take any action until we actually see that play cursor move, because if the play cursor hasn't moved, then we are in a situation where we really don't know what's going on and we probably shouldn't be touching the buffer. Excuse me. Still sick. Getting better, but still sick. It is true. Okay, so that's something that we need to take a look at, certainly. Something to think about. The other thing that I want to do, and the first thing that I think we're going to do here, is that a square wave is actually not a particularly good wave for hearing errors. And the reason it's a very harsh wave, you can actually just tell just by looking at the square wave. And for those of you who were here yesterday, you know what the square wave is, but I'll just bring it up again just to refresh your memory. A square wave is basically a completely harsh cut. It's full on, followed by full off, followed by full on, or I should say full positive, followed by full negative. And if you think about that, that basically introduces this really hard, it's very unnatural. That's not something that you're probably ever actually going to see in the real world, right? Sound is a lot smoother normally. And so that's just a bad thing to test against. We don't really know what that should sound like intuitively. We probably can't hear errors in it very well. So the first thing that I want to do, and I didn't do this originally because I didn't want to complicate the explanation by starting to talk about transcendentals and things like this, is we're going to actually switch to a sine wave. A sine wave obviously is very familiar to most people, and you've probably seen it if you've ever taken high school math, at least in the United States. Typically everyone has to go through trigonometry, which means that you'll have seen something like a sine wave. A sine wave is basically a continuous periodic wave that just kind of loops up and down, very smooth, very continuous, and it sounds to your ear like a very pure tone. It is like the most pure sounding tone that you can really hear. It's like this perfect, smooth, no noise, no harshness to it. It's like a very warm, pure tone. And so what I'd like to do is basically just first switch over to a sine wave, because I think we'll have an easier time hearing the errors if we switch over to a sine wave for our sound output. So that's the first thing we're going to do. And in order to do that, we need to change the way that we're computing our sample value. Because remember, our sample value is currently being computed as a square wave. So we're going to go ahead and change this square wave period to just wave period, and a half square wave period to half wave period, because now we're going to actually not be talking about a square wave anymore. We are going to be talking about a sine wave. So if we actually go in here, the first thing that we have to understand is basically we're going to be seeing floating point numbers for the first time. And I'm not going to try to explain them fully here because we don't really need to understand them fully to do this. But there's something that's going to come up again in the stream actually fairly soon that we will have to start understanding in a little more detail. So this is just your first introduction to them. Don't worry about them too much, but try to start getting acquainted. Basically what I like to do, like everything else, is I like to have a type def for them because I like to be able to specify the size explicitly. Basically the types that I use for them are real 32 and real 64. Those are the two types that I use. And basically they correspond to the two built-in types for C and C++, which are float and double. Now a float is 32 bits wide and a double is 64 bits wide on the machines that we're talking about here. And basically that is usually true across a lot of platforms because there's a thing called the IEEE standard for floating point, and it actually specifies how the floats work and how they work in 32-bit. So you can actually take a look here. If you look this up, you can actually see there's a whole spec for these sorts of things that you can look at. It's not it's basically a very rigorously defined thing, I guess is how I would say it. So there's not a lot of flexibility across platforms with how the actual math works out when you're operating on these values. There actually is a very rigorous definition for how all the math has to be worked out. There's reasons behind all of it. We'll refer to some of it as we go through the stream, But a lot of the minutia here, there's a lot of minutia to floating point math that we'll probably never get to. Stuff that you only really care about in scientific computing or very delicate numerical algorithms where you care about stuff like, is something positive or negative zero? And yes, ladies and gentlemen, there is such a thing as positive or negative zero in the IEEE, and there's good reasons for it too, reasons that I don't necessarily pretend to understand very deeply, because some of the people who came up with this stuff were really crazy good at thinking about computer math and all of the ramifications of it for computing actual math. It's scary how much thought went into some of these things. And if you're into that sort of stuff, I highly recommend reading about the history of it and so on. It's actually very fascinating, but we're not going to go into that today or possibly ever. We're only going to kind of touch on them a little bit further out. So we're going to go ahead and include math.h, and this is just something, again, for test code. In the actual code that we actually write, we are probably going to take the time to not use the C runtime library for floating point operations that we're about to use the C runtime library for here. They're built in. Basically, if you want to call sine, if you want to call cosine, if you want to call tangent or antitangent, these sorts of things, they are actually built into the C runtime library, and sometimes they are built into the CPU. But some of them aren't built into the CPU, and one of the things that I kept harping on the stream over and over is that we're not going to use any libraries. And so even though some of these may be built in, some of them may not be built in, etc., what I want to do sort of in the stream proper after we get out of the platform layer is I want to actually show you how to implement some of these things yourself directly. So for at the moment, because we're focusing on sound, we're going to go ahead and allow ourselves to use that sine function for testing purposes, but when we actually go to implement the actual game, when we want to sine and cosine, I'm going to show you a little bit more about how those things are computed and the things that we should actually be aware of to implement them ourselves. I think it'd be a good idea. I realize it's a little bit overkill. A lot of people watching the stream are probably like, that's ridiculous, but you know, like I said, we're trying to use no libraries, so we'll probably actually not use any libraries. But for test code, you're allowed to call anything you want if you want to. Test code is just basically about testing stuff as efficiently as possible. And so if you've got it, you can use it. That is totally fine. Much like here in the platform layer, we use all sorts of things like output debug string. When you're on a particular platform, always feel free to use whatever that platform gives you to get your test code up and running and that sort of stuff. That is always totally fine, obviously, as well. And in general, like I've said, sorry to harp on this, but using libraries and stuff is fine too. Some people have been getting the impression that I say don't ever use libraries or anything like that. That's not true. The only reason we're not using any libraries on this stream is just because I want to show you how everything's done, not because I think there's anything wrong with libraries. There are a couple libraries that I even like and I use. Sean Barrett's libraries, the STB libraries, I've used in code many times and I love them. So yeah, there's nothing wrong with libraries. It's just we're going to be trying to make sure that we really don't rely on any in our actual game code, because I just want to show you how to build your own stuff. Okay. So we want to compute a sample value that's going to be a sine wave. So basically how this actually works is we're going to have one of our floating point values here that's going to be the sine value that comes back, right? We're going to have a sine value that's in floating point. The reason that we're going to do that is because all of these advanced math functions, the transcendental sine, cosine, tangent, those sorts of things, they do not operate on integers by default. Because all of these things, the mathematical definition for them is stuff like, sine returns a value between -1 and 1. That is just the mathematical definition typically of how sine works. You pass in an angle, right? If you remember your trigonometry, you pass in an angle. The angle is usually in radians, but you could also think of the angle as being in degrees and then convert to radians. Computers work in radians, but sometimes math classes teach things in degrees, so 6 and 1/2 doesn't know the other. You can always convert between them. But point being, you pass in an angle in radians, and you get back from that a value between -1 and 1. So obviously an integer would not be a very useful thing to return this in, because it only has -1, 0, and 1 as values, and you need all the values in between. You need all those fractional values. Now, one thing they could have done is decided to multiply it out so that it actually returned like -4 billion to +4 billion, or sorry, -2 billion to +2 billion as the values, and then, blah, blah, blah. But because if you're using sine and cosine, you're almost always dealing with very mathy code, and mathy code is almost always written in floating point. all of the math functions natively work in floating point as well. And we are mostly going to be doing our math in floating point too, because modern processors have a lot of horsepower designed to facilitate floating point math, and we want to take advantage of that. It used to be, in the old days, in fact, when I was growing up, my favorite computer to program on. Again, this is a very meandering stream today. That's by design. I apologize for boring people with my stories, but I'm going to tell them anyway. Sometimes it's the coffee. I had some coffee this morning. Makes me very loquacious. It's true. I think coffee has a similar effect to alcohol, perhaps, where you start to think your stories are really interesting, even though they're no more interesting than before you drank the coffee. But here's the thing. I used to have an Amiga computer. I've said this on the stream before, and I loved programming on that thing. But one of the interesting things about computers at that time, especially home computers at that time, they oftentimes didn't have any floating point operations in the actual hardware. The 68,000 CPU, which is what powered the original Amigas, Amiga 500, Amiga 2000, Amiga 1000, those did not have what's called a floating point unit, an FPU. They did not have one in there, and so they actually could not natively compute anything in floating point. All of their computations were done with integer, and if you wanted floating point operations, that meant it had to be implemented essentially using integer arithmetic that simulated the floating point math, which is obviously very expensive, much more expensive, because you're doing a lot of operations to simulate essentially one operation. You want to do a floating point multiply, and you got to do a bunch of integer work to make that happen. You're basically doing what the CPU would be doing internally. So in the old days, people used what was called fixed point. And what fixed point is it's basically a way of dividing up your integer into pieces. And you know what? Because it sort of worked, and I'm not going to use the word so well, because so well would be kind of overstating the case, but because it worked at all, let's just use that phrase, because it worked at all for our audio the other day when I was drawing out to you what we were doing, I'm going to go ahead and go over here to the diagram and just kind of draw out for you what I mean so that it's a little clearer. So if you imagine, basically we've got, I like drawing these little hash marks with either side. As you know, everything can be that. This was a sound buffer yesterday. Today this is going to be a 32-bit integer, right? So basically what happens in a 32-bit integer, right, and you know, you usually look at them, this is going to be the 31st bit up here, and this is going to be the 0th bit down here, right? That's where we're at. And we've got, we can basically chunk this up into even parts that are 8 bits each. This is byte 0, right? This is byte 1, byte 2, and byte 3, right? That's what we've got, basically. These are bytes here, each one's 8 bits. So if you take a look at this 32-bit integer, there's a number of ways that we could imagine that it was divided, right? What we've been doing so far is we've either been assuming that it's unsigned, which means that all of the bits just act together to give you one value. So there's the 0 bit, there's the 1 bit, there's the bit that if it is set, it equals 1, then the one that's equal 2, then 4, then 8, then 16, 32, 64, 128, 56, 512, etc., right? And you add all those up together, and that's your number. So if you have the bottom 3-bit set, you know that your actual value is the 1 plus the 2 plus the 4, right? We went over this in the intro to C-Stream. Hopefully everyone's familiar with the binary encoding there. That's how we've been doing it. And then sometimes we've used negative numbers, and negative numbers use what's called 2's complement, and that's basically where you have the high bit is set, you know it's a negative number, and then the rest of these are encoded in a way that basically makes so the math still works out for negatives. You interpret them slightly differently. We didn't actually talk about 2's complement on the stream. We should probably do a stream about that at some point, but it's not germane at the moment, so we're just going to skip that. Point being, that's all we've done, though, so far. Now, there's other things we could have done with our 32-bit integer. Let's say that we actually wanted to store some fractional precision here. Let's say that we wanted to do something like have a number, so we have a number, right, like we would in math, with a decimal point, and then a fractional part that comes after it, right? Well, one thing that we could do, if we wanted to do that, is we could imagine that we just separated up our bits into this part, right, and this part. So we could say, we could just arbitrarily say, okay, let's say the bottom 8 bits are the fraction, right? And then the top 24 bits are the number, right? So this is a number up here, this 24-bit number, which means it can be up to like 16 million, right? So we have 0 to 16 million in the top part. And then down here, we have 0 to 256. And so we just assume that we have, oh, well, 255, I should say, right? So we just assume that we have whatever this number is in the top 24 bits, And then we have a fraction that is essentially whatever this number is. We'll call this number f, let's say, for fraction. We have f over 256. So our number is whatever our number is in the top 24 bits. It's this thing, plus whatever this thing was divided by 256. You see how we could encode it that way. And you can see how that'd be pretty easy to extract as well. If we wanted to just know what the top number is, we could just shift this down by 8, right? So the whole number, we'll call the entire number w, let's say. If the whole number was shifted down by 8 bits, it would knock out the fraction and leave us with just the actual number, so we know our whole number very quickly. That's called truncation. It gets rid of the fraction entirely, right? It just gives us back the number. We could also round the number if we wanted to. We could add, right, half of this. We could add 256 over 2, or whatever, right? Actually, it's actually technically 255 over 2, so it'd be 127, right? We could add 127 to the bottom, which would mean that if it was 128 or higher, right, it would wrap and add 1 into here. It would carry into there, right? And that would increment our whole number by 1. If it wasn't, if it was less than that, then it wouldn't carry. It would just stay in here when we did the add. We could do that add, then do the shift, which would have the effect of rounding, right? So truncation would be this. This is truncation right here, right? That's truncation. And rounding is just w plus the fraction total over 2, then we shift it down by 8, right? Hopefully, this is not a complete explanation either. Hopefully that kind of makes some sense, right? Do you see how that could kind of work? And then we're basically doing a bunch of math on numbers that are encoded this way. There's some other stuff you have to do with multiplication. You have to worry about the shifting because you've got an extra decimal place and all this sort of stuff. I won't really cover that. But basically, this is called fixed point, right? Oops, fixed point. Fixed point math. And this was something that people did back in the day in order to avoid doing really expensive floating point math when they didn't have a floating point coprocessor. That is fixed point. That's how that works. It's called fixed point because you have set an arbitrary fixed place where the decimal occurs in your number. That is how it works. You can never have more than 256 levels of your fraction, no matter what the number is, and you can never have any more than 6 million here because you only had 24 bits. So wherever you pick, you could change that decision by moving this around, but whatever the line is that you pick to write your math at, you basically are fixing the amount of fraction versus the size of the number that you can have. Does that make sense? So what floating point is floating point is a more powerful representation that basically allows you more flexibility at the cost of having the precision of your operations vary depending on the values involved. And basically what it is it's a different way of dividing up those bits. So floating point works completely differently. It's actually completely different conceptually than fixed point, really. How it works is it's divided up in a way that looks sort of like this. We have a thing called the mantissa, which goes down here, and this is basically a number that tells us only a fraction of 1. So it's basically a number between 0 and 1. That is how that works essentially in here. I shouldn't say it. I'm not sure how to explain this well. It's not really a number between 0 and 1. It's basically a value. Here's how. You know what? Here's how I'll say it. This is much clearer to what it actually is. If you imagine a number that's like 1 point something, and there's a decimal out here, right? So we basically have 1.2, 3, 5, 9, 4, 7, 8, 6, whatever, right? Some fraction out here. The mantissa is a bunch of bits that stores this. It's the part that stores the fraction. The 1 is not stored. It's just assumed to be there. So it's just the fractional part. That's the mantissa, a fraction of this 1, okay? So the mantissa is here, and then we have the exponent up here. This is an exponent. So basically this is, if you know like an exponent, if you have something like x to the 4th power, that is an exponent, right? It's something that raises something to the power of. So we have the exponent, and then we have the sign bit. The sign bit is either 0 or 1, depending if the thing is negative or positive, right? That's all that means. The exponent is a power of 2 that says how big this number is. So essentially, whatever this exponent is here, whatever this value is, it's basically saying if this is n, it's 2 to the n. That's what it is, right? And then this is the actual fractional value. What this allows you to do is it basically allows you to separate the degree of precision you have in specifying the number, which is always going to be however big the mantissa is, from the scale of the value, which is specified here in the exponent. So this tells you the magnitude of the number expressed as a power of 2. And this tells you the actual value of the number, which will become bigger or smaller depending on what this is. So if this is high, right? If the exponent is high, then basically the mantissa encodes a much lower amount of precision for the value, right? Because whatever the fraction is, however much precision the fraction has in here, you're basically moving it up to a place in the number based on this n, right? So let's say this n is like 50 or something like that. Then you're taking 2 to the 50th, right? That's a very high number, and you're multiplying this other value by that. So even if it had a lot of fractional bits, even though that fraction is very specific, it's moving up into the whole number part because of this giant multiplication. On the other hand, right, if this number is negative, right, because this exponent can be negative as well, right? If this number is negative, then you're moving it down. Because again, 2 to like the negative n, right, 2 to a negative number is basically creating the opposite. It's making fractional values. It's making, it's dividing out, because that's the way exponents work. Again, this is just, I'm assuming you basically know exponents here. So what you're doing with that exponent is you're sort of sliding this decimal point around. So what ends up happening with the floating point representation is you basically have a situation where you've got 1.2, 3, 5, 9, 8, 4, 7, whatever. You've got some fractional value here, and you're taking the point with that exponent. This is specified in the mantissa, right? So this is just represented in the mantissa. You're taking this point and you're sliding it by that exponent, however many places the exponent is. So if the exponent is negative, right, you're sliding it this way. You're making it more of a fraction. You're making it 0.00000001 or something, right? If the exponent is negative, this is a negative exponent. And if the exponent is positive, you're sliding it this way, right? So you're making it bigger. You're making it 1 million something blah, 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 right, or whatever. And that's why it's called floating point, is because the decimal point essentially floats. It's no longer fixed. It's not fixed point anymore. It's floating point. And what that means is when you do math with floating point, you're basically always guaranteed the same amount of relative precision no matter what your values are, right? You're always essentially getting the same amount of significant figures, if you will, right? If you ever saw that term. You're sort of getting that sort of equivalent of scientific significant figures in some sense, where you're saying however many bits of mantissa the floating point format you're using happens to have. And again, there's 32-bit floating point, 64-bit floating point, so the size, the precision varies depending on how big the total thing was. Basically, you're getting a certain amount of significant figures, which depends on the mantissa size, a certain degree of scale possibilities, depending on how many bits are in the exponent, right? And then you can do math at any scale allowed by that exponent will have the same number of relative significant figures. So if it's a very high number, right? Let's say, it's some, again, we have 2, 3, 5, 9, 8, 4, 7, whatever, and this is some really big number, right? It's some number that's huge like this. We're still getting the same number of significant figures, essentially, right, here, as we would if we encoded that in a different way that was very, very small, right? If we used a different exponent for it, right? Here's the same number, but we've slid it down quite a bit, right? We have the exact same number of significant figures no matter what the scale is. We're never getting any more than that. Once we get up to the scale, we can't even encode what the values are that go all the way to the decimal point. There might be tons of zeros here, and we have no idea what they should have been because we can't encode that. And same as here, we can't know what any of these things are because we've pushed it down too far. But that's basically how that works, right? Now, again, I'm drawing this all in decimal. I'm writing 0.000 as if they're decimals, and then these are all decimal numbers, right? And that's not really the case because this is all binary. So really these would be things like 0.0010100101, that sort of stuff. But you get the idea. It works exactly the same. You're still moving a decimal point around that has to do with that. So hopefully that makes some sense. Oh, I'm sorry. I just checked the stream. I guess I'm talking too loudly today. I should quiet myself down, perhaps. Maybe I'm getting a little too coffeeed up. I'm getting a little too caffeine-y, and I'm clipping. Sorry about that. I'll try to calm down, make a much calmer tone. Okay, so basically that is basically the way that floating point works. And we'll talk about this a little bit more as we go, so I can kind of explain more what's going on with the floating point numbers and why you have to understand some of these things, because obviously this is all kind of minutia. The processor is doing it for you now. So basically what we are able to do with modern processors that we couldn't do, say, on the Amiga, which didn't have an FPU, they actually later added one in the 68030. So if you bought like an Amiga 3000, which was a later version of the Amigas, they had FPUs that could do some floating point math. Nowadays, everything does floating point math. Your graphics card does floating point math, your CPU can do floating point math, and in fact, most of the computing horsepower in your computer is often dedicated to doing floating point math, because floating point math is where most calculations happen now. Certainly all 3D graphics runs through floating point math. At almost every stage of the pipeline is very heavily floating point now. Certainly all scientific computing almost always uses floating point math, although there are certain cases where integer math gets used and so on. So floating point math is one of the most important features of a CPU now. Even though they couldn't do them in the old days, they now have tons of horsepower for it. So again, even though we're taking a very handmade approach to this, fixed point, even in that case, is a very bad idea, because really what you want to be doing now, if you're trying to be efficient and trying to be down to the CPU level, is you want to be using floating point, because that is where the horsepower exists at almost every level of computing now, is that floating point. We're going to encounter some problems on the Raspberry Pi, I think, because I know there's some delicacies with floating point there. So that'll be a bit of a battle, certainly, but for the most part, in any modern thing that you would ship a game on, there is a ton of floating point horsepower. Even mobile devices have a ton of floating point horsepower. All right, we're gonna end that there, close our MS Paint session, and we are gonna go back to creating our sine wave. Now, a sine wave is obviously very simple. I showed you what it looked like. All we need to do to get our sine value is we just have to call sine, and we have to call it with where we were in the period of the sine function, basically. Now, there's two versions of sine. I can show you what they are. There's sine and sine f. I'm hoping if I do sine f, it'll come up with both of them. Yeah, here we go. Here's in the MSDN documentation. So you can see here's the sine functions, right? There's basically a sine f, which takes a float and returns a float. Those are 32. That's a 32-bit sine. And then there's a double sine, which is a 64-bit version of the same thing. There's 64-bit floating point when you want more precision, and there's 32-bit when you don't need as much. We will probably never really use 64-bit precision for most stuff in the game, but it's worth noting that it's there. It's slower, always, pretty much. It's very rare that you can do 64-bit floating point math as fast as you can do 32-bit floating point math. Usually that's true these days because basically of SIMD. We won't get into that too much, but basically you tend to be able to do twice as many floating point operations as you can double operations because of the way that the processors work nowadays. So it's usually best not to go double unless you really know you need that extra precision. And in this case, we definitely don't, and for most of the game, we aren't going to need it, so you probably want to stay away from that. So we're going to call sine f, and we basically need to know where we are. We basically are in some position in the sine wave, which typically in math is called t. Usually t is the value that's kind of the running time value for your sine. So we need to compute whatever that is. But once we get our sine value back, remember our sine value is going to be a number between -1 and 1. But we actually want a value that goes between tone volume and negative tone volume. So what we need to do is we basically need to cast to an int16, but we first need to take our sine value and we need to multiply it by the volume so that it will take it from a -1 to 1 version of our sine value And why is it doing that? My keyboard is overzealous today. I don't know why. That's very interesting. Is that, there we go, it's a little bit better. Okay, so basically what we're trying to do is basically just scale our sine wave from -1 to 1 up to the tone volume so that it can be mapped into the 16-bit space properly, if that makes sense. Okay, so basically what we want to do here is we want to say, okay, we're going to do that. We're going to let that go ahead and put that back into our sample value. We don't care about rounding at this point, so we're going to ignore, we're not even going to talk about that at the moment. And basically, we don't need this anymore, which is our square wave generator. And we'll go ahead and copy this down here after we're done. We need to collapse these two loops eventually, as our to-do says. So basically, in our T, we know that we already have a running sample index, which just keeps going up and up and up. So that is essentially our T value. But if we were to use that as the T value, the period of sine, right, I believe is pi, right? Let's take a look here. So sine, if you take a look at the actual scale of this thing, you can see that the period, well, the half period is pi, right? So 1 cycle is pi, and 2 cycles is 2 pi. So our half period, I guess we don't have to care anymore about a half period. We can literally just go with our period now. Since our period is going to be 2 pi, right? Basically what we want to do is say, as this thing goes up to whatever the actual period was going to be, which we computed, right? Here's our wave period. Whatever our, and we don't actually need this value anymore. The half wave period just doesn't need to be used. So whatever our wave period is, basically we have to say the the running sample index divided by the wave period, right, is going to map that into a number from 0 to 1. You know, as we go through the wave, it'll be 0, 1, 2, 3, 4, just like we did before, the divide that tells us where we are in the period. But what we want to do here is we want to actually convert these to floating point first, so that now we actually have smooth values that run from 0 to 1 fractional as we go through. I may have to diagram this out for you. I realize this is a little complicated and we haven't done stuff like this before. So I'm going to actually, I'm going to do a to-do, draw this out for people so they can see it. And then we need to multiply by the period we actually wanted, which was 2 pi. Now, we don't actually have a value for pi yet. So the other thing we need to do is actually do a pound define for pi. So here is our pi 32. That's going to be some real 32 value. And basically what we need to do is get the digits of pi and put them in there. Now, I don't know exactly how many digits we need for a floating point pi. I'm going to go ahead and see if that's enough. Let's see here. Why do I always reverse the order of things? Yeah, doesn't matter, compiler always catches it, so it's good. So basically what we're doing here is we're just transforming the period of running sample index into the period of sine. We're calling sine, we're multiplying it by the tone volume, and that's our sample value. Should be pretty straightforward. I don't think there'll be too much confusion there. But again, finicky code. I make a lot of stupid errors when I write code like this, even when I'm not streaming. So we may have to do a little bit of debugging here. Everyone brace your ears. It is time to listen to our sound, which could be totally messed up. Let's see what it sounds like. Why am I not hearing anything? What did I do? Did I do something? Oh, yes. We forgot to actually increment our value. I should just leave that down there as we play with this. There we go. Let's see. There we go. So I can hear immediately a scratchiness in that, right? And that means, I mean, obviously we could have messed up our sine value, certainly, but assuming that that is actually, assuming that that scratchiness is actually in there without the fact that we've messed up the sine value, that is sort of revealing the fact that there is clearly a bug in our wave output, which is what I wanted to do, because I was pretty sure there was, but you know, I wanted to actually make sure that we knew that first. So now we can actually go about starting to debug this. The first thing to do is to verify that our sine wave makes some sense. Okay. So one thing we could actually do if we wanted to is actually draw the sine wave out on the screen, which is probably what I would do in a normal circumstance. And I'm not sure if I want to do it now only because we'll have to sort of explain a bunch of drawing things to get there. But the other thing that we can do is we can kind of look at this code inspection-wise First of all, step through it once, make sure that we understand what's going on. The other thing we can do is not fill the buffer. So basically, we know we had a 1 second buffer. So the very first thing I'm going to do is just never fill it again. So basically what I'm going to do here is this sound is playing, this thing that says if not sound is playing. That sound is playing, I'm just going to use that as a latch to only update the buffer once. So basically what I'm going to do is here is say, instead of calling get current position, I'm going to say if the sound is not playing and you were able to get that cursor position, then go ahead and fill that buffer, right? So basically I'm just going to do this. So what you can hear now, at least I hope you can hear this, if you can hear it, we hear only one skip. Do you hear that? Solid tone and skip. And how far is it apart? 1 second? 1, 2, 3, 4, 5. You hear that? Right? So when you hear that, what we now know, what that has determined, right, is that we have a bug in how we fill the buffers where the sine lines up when we fill those buffers, right? We know that our sine wave is actually outputting correctly because our sine wave, when we listen to it, when we listen to the sine wave just filling the buffer once, it sounds like a pure tone correct, and the only time it has a skip is at the end of that 1 second buffer, which is where it should skip because we didn't do anything to make sure that the sine wave wraps properly from the end of the buffer to the beginning. So there's a hard gap there, right? So basically we've now determined rather definitively that at least our sine output, this code right here, is working properly. What's not working properly is either the way that these two things are gapped together, because remember we're only testing one path. In fact, we can sort of see that here. When we come through and do this the first time, right, when we get this back, our region, our two region sizes, let's take a look at those here. Region 1 size, region 2 size. You can see that because we're locking the whole buffer that first time through because it's not playing yet and we're just filling the whole thing up, you can see that we only do one region fill. So we're only doing this fill. So we could have a bug here as well. That's entirely on the table. We have not ruled that out. But we know that we either have a bug there or we have a bug in how this stuff is updating, because we're basically saying when we start to actually fill the buffer up incrementally afterwards, we're introducing a lot of skips that should not be there, right? Does that make sense? And so there's a bunch of things that could be wrong about that. One is that we could be doing this fill wrong. One is that we could be incrementing our sample index wrong, so that we're thinking we should be, the place that we're actually writing into is not the place that we should actually be according to where we are on the sine wave. There's a lot of things we could be doing wrong. And so now we have to kind of go figure out what those are. Okay. So, first thing we want to check is just let's go through the code and just verify that we actually think we know what's going on here. We know we have basically a buffer that's going to be 48,000 samples long, which is going to be 48,000 times 4 because in terms of bytes, right? That's the bytes per sample. So when we init dsound, we're expecting to pass 48,000 here and 48,000 times 4 here. So let's go ahead and just step in, and we'll kind of walk through the code. We'll sort of analyze it line by line and make sure that we understand what's going on. Oops, I had to actually start it running again. There we go. So when we pass it in here, let's take a look. That should be 48,000. I'm going to switch out a hexadecimal display here. Samples per second should be 48,000. It is. Secondary buffer size should be 4 times that. That looks about right. 4 times 48,000. Yep, that looks right. That's what we expect. So our buffer is 1 second long, and it's playing at 48 kilohertz, which is what we wanted. We come in here, we process our messages, and then we're going to go here to fill our buffer. The sound is not playing yet. We go in here to fill the buffer. Our running sample index should be 0, and it is. Our bytes per sample should be 4. Now why is this not parenthetical though? That bothers me a little bit, because that should be a parentheses right there, and that is not how I would normally write that code. So I messed that up because the operator precedence, to be honest with you, I don't even remember what the operator precedence is between these two operators. I would never leave that be. So let's double check our operator precedence there since it came up. Operator precedence C. And let's see if it's got it here. Where is the mod operator, people? Where is it? It's right there. So these are left to right. So in theory, that's not a bug, so it would have been operating properly. But I don't like that at all. I don't like to leave things like that to chance. I don't like to be the kind of person who just memorizes the operator precedence and always embeds that in the code. I think it's a lot easier for other people as well as yourself to read code that looks like that, so you know unequivocally that's what they meant, and there's no problem. Don't worry about the 5-minute warning today, people, because like I said, this was going to be a kind of meandering stream on a holiday, so we're going to go ahead and blow straight through that. There will be a Q&A. We will probably just take the whole Q&A, the whole 30 minutes normally for Q&A to finish what we were doing, just kind of get comfortable, and then we will have a Q&A after that as well. All right. So basically, we've got the bytes to lock here. That looks like a correct computation to me, the byte to lock, rather. Basically, what we're doing is we're saying whatever our sample index was times the number of bytes per sample modded by the entire buffer size should be where we are in the buffer. That seems like a solid computation to me. I feel like that is relatively straightforward. I'm going to go ahead and recompile that here, and then I am going to step back to here. And I am actually, you know what the other thing I'm going to do is I'm going to remove our check there so that we actually can step through twice. Because what I'd like to do is I'd like to verify that this wraps around to 0 again the second time through. So the first time through, we compute that byte to lock and it's 0. The second time through, I would like to verify that it's 0 again. And it is, so that's good. That's what I wanted to see, and wanted to make sure that the sample index would go up by 48K, and it did. And that all looks roughly correct. Okay, so let's move on to thinking about something else. So I think that running sample index looks kind of okay to me so far. You never do know. If the byte to lock equals the play cursor, that should only happen that one time. At the moment, like I said, it's a little iffy. We've got the to do in there, but I'm going to go ahead and try to verify that it only happens the one time. Oh no. See, look at that. We've already found a problem. Why is that happening? Why is the play cursor and the byte to lock always the same? Oh, you know, oh, that's funny. That is very interesting. So I think basically what's happening is exactly what this to-do said would happen. Basically, we are writing up to the play cursor, and then we always find that the play cursor has not advanced by the time we get through the loop the second time. That is what's happening, I think. So really, we just have to make sure that the byte to lock is behind the play cursor always, if it is not. So if it's above the play cursor, that's okay. That means the play cursor, we have sort of wrapped around it. But if we're equal to the play cursor, that's actually something that maybe we're going to have to start just not doing anything, because we're assuming that we've already caught up and we're fine. So really, that should probably look like this. So we're going to do a little bit of a hack here. If sound is playing, if sound is not playing, we're going to do that. And I'm just going to double check what that sounds like real quick. Let's see here. Okay, so that already eliminated one of our problems. You can tell that it's very different already. We still got problems, but that was definitely wrong. So all right, so let's think about this for a second. So what we should probably do is start pulling this out into a little bit less hacky, a little bit more correct code, so that we can do stuff like fill our buffer, control how we're filling our buffer a little more explicitly, so we can call it in here. So let's go ahead. I'm just going to pull this out here. I'm going to make a little struct called struct min32 sound output, and I'm just going to wrap these values up in there. I'm going to pull them out of there so that we can have a little more granular control over what's going on. So all of these sound values that we had, they're all going to come out into here, right? And I'm going to actually have those defaults set outside. So here we go in some code. We got to set up our stuff here. So if we make a Win32 sound output, this is our sound output struct, we can go ahead and then set all the values to what we were setting them to, like this. There we go. Set the wave period, set the bytes per sample, set the buffer size. There we go. And these guys now have to be based on this. There we go. So we're going to set all that stuff up. So that's good. And then we are going to go ahead and make this initialization code happen down there. So let's get rid of these because you can't actually do those. You can, funnily enough, you could actually leave those in, I think, now. I think they added, the C++ 11 standard added some abilities to specify default values like that. So you could have actually left that in there technically. So we're going to go ahead and move that down into here. So basically, we're going to create one of these, and we're going to fill it out like that. So that's good. We are going to now call Win32 init dsound with those values. So now we'll initialize them straight out of the sound output, and that's fine. And then what we'll do is we're going to make our buffer fill stuff. We're going to actually make that buffer fill stuff be something that we can call separately, and we can give it a little bit more of guidance about what we actually want to do. So this buffer fill stuff right here, basically this part right here, we are going to pull out into something that can kind of be called in different ways at different times, so that we can be a little more explicit about it and see what's going on. So let's see, Win32 fill sound buffer, like this. And that's going to take one of these sound outputs like that. There we go. And then it will take the two parameters that were passed here before, the byte to lock and the bytes to write. It'll basically pass those in here, right? See that? So we're basically just extracting that code out. Again, like I said, I'm a big fan of just pulling things out when you need them. Instead of trying to design stuff up front, you just see what the patterns are that emerge, and then you pull out. It's a good way to keep yourself in a good state, so that the code's always actually doing something useful and you're not wasting a lot of time with abstractions that don't actually do anything for you. So that's the way I like to do it. Always pull out, start with the code, pull it out. All right, so basically what we've got here is we've got a function now that'll do this fill for us, and we just need to basically reference the sound output for all the parameters that we used to use. So bytes per sample was one. We've got running sample index, that's one. We've got our wave period, that's one. Got our tone volume. That looks like about it. We've got that. We've got this. And we've got that. Okay. So that should basically give us what we had before. Let's go ahead and compile that, make sure that works. That missed a couple. There's one. There's another. And there we go. All right. So now down in here, what we need to do is we need to actually call this function, right? We need to actually call our fill function down in here, and we will do that. And there we go. Now we will call the sound output. With that, we will use our byte to lock and bytes to write. And now this should basically give us the same code with the same bug. It's just all we did was pull it out into another function. That's the only thing that we've done so far. So there's our sound output. Let's take a compile here and just fix our compile errors. Sound output. Oops. Sound output. There we go. That and that. So let's go ahead and just get that indented properly. And last but not least, there we go. So this should give us the same exact thing we had before. Same bug, same everything. Yes. And that is exactly what we get. So that's fine. All right. So now what we can do is we can make this stuff a little bit cleaner. What we can do is we can say, all right, the first time through after we init, let's go ahead and do a little bit of a fill. So let's go down here and say, all right, we've got our Win32 fill sound buffer. Let's go ahead and fill the sound buffer at startup. And then we can also do our play at startup as well. So we can kick the sound buffer off right here. That gets rid of that sound is playing variable. That's gone. And we can just basically kick it off right here. So what we're going to do is we're going to fill our sound buffer. Excuse me. We're going to fill our sound buffer, and we're basically going to pass it the first byte, and we're going to pass it, I guess we'll just do, for the bytes to write, we'll do the entire secondary buffer size. So that'll fill the buffer like we said before. Now what should happen here, again, is we should basically get exactly the thing that we got before. Let's go ahead and do this. We should get the same exact bug that we got before. Ho-ho! Now we are back to a pure tone, ladies and gentlemen. In fact, a perfectly pure tone. So basically that check there was bogus. Why was that the case? That's very interesting. Let's take a look. Oh, even better. That was just an uninitialized variable. That's all that was. That was our entirety of our bug. We forgot to do that. That was it. No other problem. That was the entirety of our sound output problem. Awesome. So basically the only problem is when we went ahead, we had our problem of not catching up to the play cursor, so we had to fix that. But when I did our test for that, we failed to actually initialize to 0. Again, one of the reasons to start pulling code out and start making things cleaner. Cleaner code has less stupid mistakes in it, right? And that's a very good way to kind of look at that. Maybe we should have actually just initialized to 0 here, but at the same time, that was actually a legitimate bug. One of the things that's interesting about that is I think maybe this might be a case where we want to start turning up our warning level as well. We should probably look at that. I'm going to write that down as maybe something to talk about next stream. Getting the warning level up to something proper, because the compiler should warn us about a lot of things. Not necessarily that one, but we're currently working without a lot of warnings turned on. And usually when I compile my code, I have a lot of warnings turned on. So something to think about. But anyway, point being, now all of our cases actually initialize the variable properly. And hey, what a surprise, our sound output works. Works perfectly. Sounds lovely, doesn't it? Listen to that pure tone. Are you loving that? Are you loving that? I'm loving that. But yeah, that's something that we want the compiler to catch for us. And so maybe, I don't know, we're kind of, I feel like we could still make this stream be limited to an hour because we've done what we wanted to do today, which is debug our sound output. That has worked. We're pretty happy about that. And one of the interesting things is if you look at the latency here, our latency is now going to be the entire buffer's worth, right? Our latency is going to be one whole buffer's worth of sound because we're always writing up to the play cursor. What we could do in the future, and what we probably will do, is write less into the buffer, right? Instead of being, we're now 1 full second latent, which would be very bad for a game because we're writing a full buffer's worth ahead of that play cursor. But what we could do is basically say, let's not do that. Let's write up to some place short of that, basically, right? Let's take a look at the play cursor. Let's move only a certain amount ahead of it, and let's write up to that. So we'll look at that a little bit later too, if that makes sense. When it comes time to actually play sound effects, that is something that we'll be looking at. So what we'll do here is we'll say to do, basically, we want to change this to using a lower latency offset from the play cursor when we actually start having sound effects, right? This sort of thing would be fine for music streaming because it's not particularly accurate in terms of latent, but basically what we want to do is change that before we get to sound effects. So I think we have actually accomplished what we wanted to do for the day. Even though it was a meandering stream, we actually did exactly what we wanted. So that's pretty exciting. The only thing I do want to note is to do implement Sine ourselves, because that would be nice. If you notice, if we go ahead and remove math.h here, you will notice we get an undefined identifier error because there is no Sine f actually implemented. So what I'd like to do is eventually implement that ourselves. We can look to, if we go in here to the Sine code, where is it? Let's see here, fill buffer. If we go in here and take a look at what it does, we can step into the assembly language and actually take a look at what that's going to do. So if you take a look here, it literally does call a function called sinef, right? I don't know if you can see that there. Let's take a look here. I'll be a little bit more explicit. We just called that one. Let's go back around the loop. Where's our jump? Jump, people, jump. There it is. So we jump back to top of the loop. We come down here, and you can see we call into this sinef function. Here is the sinef function. Oh, well, no, it's asm, and I guess it's not going to show us the sinef function because we don't have the source. But we can look at the raw assembly for it. Let's take a look here. Doing a compare, doing a load, doing a bunch of testing, doing a bunch of mulls, blah, 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 blah. You can look at that. That's a pretty expensive sine, actually, it looks like. I don't know if that's the most... We may want to... we may be able to implement a more efficient sine because we know that we only care about certain things as well. So that's definitely something that we probably don't want to just leave to chance. So we will probably do something with that ourselves. All right. Anyway, I think that is basically all we wanted to get done today. We will do timers tomorrow, and then finally on next week we'll actually... I think we're in really good shape. Next week we should be out of Windows code. We still will probably do a little bit with file loading in the Windows code, and we'll be massaging the Windows platform layer a bit next week as we go through it. But I think that's it. Tomorrow we'll do timers, and then we are good to go. Ladies and gentlemen, we have been remarkably on time with this stream. The first day, not the first day, the second day, I think, was the only day we really didn't get to as much as we wanted to. This has been amazing. I don't know. Give yourselves a pat on the back for our punctuality. I think that's about it. So let's go ahead. Let's go ahead and go to the day 9 Q&A. Yeah, let's keep our streak going here. Let's take a look. Uplink coder. Indeed, this bug could not have happened. D always initializes variables. Yes, and I actually try to do that myself as well a lot of times. The only problem is sometimes. So what I like to do a lot of times, and you know, I'm going to go ahead and point this out here actually in our code. You'll notice what I like to do a lot of times is stuff like this. I like to always just initialize to 0 at the opening. In code that's not performance critical, I like to just initialize to 0 because I feel like it catches a lot of bugs for you. And you just always assume that things are 0, so you don't even clear values that are going to be 0, and you try to make as many values default to 0 as possible. A very good way to do things. So I like that. I would probably like that aspect of D. I have not programmed D myself, but I do think that's a good idea. What would be nice is something basically where you always assume that values are initialized, and then you ask for them not to be initialized would be the better way to go. So that in a case where you care about the performance and don't want default values, you just say that. That's probably something that would be a good idea in languages, or at least give the programmer the ability to basically say with a struct, here is, I expect this to be initialized to 0 all the time unless the person asks not for it to be, would be a nice keyword, for example. Now, the thing that I do want to emphasize here, though, is that this is not really about catching a bug. What I wanted the compiler to do was not to initialize bytes to write, because we still had a bug, in a sense. Yes, 0 happened to be the right value there, so it seems like it would have been catching the bug, but actually what would have happened is it would just been hiding the fact that our logic was buggy. And so what I would rather have had happen there, and what I think the compiler would have done if we had turned our warning level up, which is why I wrote that down as something to do very soon, maybe Monday we'll do that, is what I want the compiler to do is to tell me that there was a hole in the logic. Tell me not all paths initialize bytes to write before it's used. That would have actually been what I want. I don't want to silently initialize the value and hide the fact that our logic was buggy, because our logic was buggy. We did this, right? We did is sound playing or whatever, something like this, right? We did a thing where we typed in something here, but we didn't have an else. I wanted to tell me that else was missing. That's what I actually wanted. And I think the C compiler will actually do that most of the time on a higher warning level, which is kind of why I brought that up. That's the thing we actually want the compiler to do for us, not silently initialize the value, because this value doesn't have a default value. It needs a specific value for every possible case. And I want the compiler to hold us to that and to say, you've got a bug here if you didn't initialize it in every case. That's what I actually want. And that is why I didn't write this to begin with, because I actually didn't want that. So that's something to keep in mind there. Let's take a look at what we've got in the stream. I'm going to blow my nose. I apologize. I am still sick. It is true. Let's see. Okay. Starting back at the beginning. Blah, blah, blah. Let's see. How do you know that byte to lock is far enough ahead of the play cursor? So we don't really know anything about it yet. All we know is that we have a 1 second long buffer, and we're updating our buffer every frame, which means that basically our game would have to stall for an entire second in order for the play cursor to loop us. So we will never know, and that is one of the bad parts of using direct sound that may be fixed in later versions of the API, but that was even fixed in wave out, which was actually the older API, but that you can't use for various other reasons. Basically, you do have a problem that if you did stall for 1 second, you wouldn't know. It would, if the buffer wrapped, if the play cursor wrapped around in the time it took you to get around to another frame, you would be totally busted. You would have no idea what went on. And so that is one argument too. You know, we could go up here and say, you know, is 1 second enough, right? You know, should we actually say, you know, maybe make this like 10 seconds, you know, or 30 seconds? How about 60 seconds? Make it a minute, right? Maybe make it so long that there's no conceivable way, no matter what happened, the game could ever pause for that long, so that we can always see very clearly where that play cursor is. And that's something to think about. Could we force multiple regions by setting a maximum buffer lock size to be a fraction of the sound buffer? Sorry, I'm not sure I understand that question. Let's see. Sorry, just reading through everything. Try W4 if it's not too much trouble, W3. We'll talk about that on Monday. I wanted to wait until I explain how warnings work and how you turn them on and off and stuff, so we'll get to that. Let's see. Where do I look for standard C function documentation like printf or size of? Yeah, and like Sine, for example. So typically you should actually be able to do MSDN printf, and you can actually still use the MSDN for that. It's got them all in there. You can also look in other places, like when you just search for printf, you will get a C++ reference that comes up, usually. So you can see that there as well. But MSDN is actually perfectly fine for looking that stuff up as well. If that makes sense. Let's take a look. I think you can now remove if byte lock equals play cursor check, it will be handled by the else case. Let's take a look. Yes, I believe that's correct, because if there, yes, you're right. We could just do this because now, since we're computing everything, we're doing the fill outside, we should basically always be correct. Like we were, that's how we wrote it initially, but we added that thing in there as kind of a hack to fill the buffer. Let's listen very carefully. Okay. I guess the other thing we could do is while we're on stream here, if I go to OBS settings, I don't actually know if I can change these offhand, but basically, is there some way to change the volume that's of the game coming out? We could test that on the stream. Maybe we'll do that in a separate test stream. I'll just write that down. Basically, like audio volume in OBS. That's something to think about because people are saying it's too loud or whatever. So we probably want to take care of that, especially when we're not working on sound code. We don't want that blasting every time we play something. So that's something to think about. Okay. Let's minimize that again. Will we use the sign in the actual game? No. We'll be playing, we probably will never use the sign value in the actual game. Is autocomplete IntelliSense a bad idea for a programmer? You and John do not seem to use it. Well, I don't think IntelliSense is a bad thing. I do use autocomplete. So I use basically, you know, I do bytes to write and hit tab or something. I do that, right, a lot, which is sort of like IntelliSense. But the reason that I don't like IntelliSense in Visual Studio is I hate the way that the input actually works. With that, it locks up your up and down arrow in a bad way. So basically, I don't think that's necessarily a bad thing. I would just say, if you can, and I've never looked into this, but if you can and you're in Visual Studio, I would say look into rebinding the keys a little bit there if you can. I don't know if IntelliSense lets you do that, but if you can, rebind the keys so that it's not locking up your arrow keys. If you could do something there. But I don't think IntelliSense is necessarily bad. I don't know that it's necessarily all that useful, though, either. Let's see. I got to do a better job of keeping my place in the stream. I need like a little tool that lets me know where we were. So we just asked the you and John did not seem to use it one. Where is that? There it is. Okay. let's see. I don't think it had to do with uninitialized variable. Wouldn't that mean you would do a huge writing past the end of the buffer? I think it's because you were overwriting the region between the play cursor and the right cursor. So yes, I mean, technically that is what was happening, but it was because of the uninitialized variable. What we wanted to do was write 0 bytes in the case where the play cursor and the byte to lock were at the same place, because there was no need to write anymore. We'd caught up. But what we were doing instead was writing an undefined number of bytes, right? We were writing some whatever the value of bytes to write actually happened to be, garbage, right? We were writing that many, essentially. And of course, it didn't overwrite the end of the buffer, because when we call lock, direct sound will clip that number down to the buffer size, presumably, or something else will happen there. So basically, we were getting a cascading failure from the fact that this value wasn't initialized. And it was causing us to do a write when we didn't want to actually do one at all. Our logic was supposed to say don't do the write, and that was the initialized variable that was causing that problem. Excuse me. Still quite sick, unfortunately. Hoping this will go away by tomorrow, maybe. I was feeling a little bit better today, so I was hoping it would start to lessen up. Anyway. Is it possible for bits to spill over to variables in neighboring variables when bit shifting ints or something like... Okay, I see what you're saying. The answer is no. So the reason that bits cannot spill in when you're doing shifts and stuff like that is because when you are doing things like that, you have to remember that the assembly language is doing very specific things. So basically, when we come in here, let's take... let me type a little example in here for you to answer your question more specifically. So let's say you want to know if I have something like this and this, right? You want to know if repeatedly shifting X will accidentally get into Y, right? So if I do something like this, right? If I shift this up 1, how many times can I do that before it shifts into Y? Something like that, right? That's what you're asking, essentially, if that makes sense. So what happens in this circumstance is you have to remember that these things are on the stack, yes, and they are next to each other. That's also true. So if I look at these two things, and I look at the address of X and I look at the address of Y, you will note that they are, sort of close to each other. They're a little further apart than you may have expected, right? They're not right next to each other. They're actually quite a bit apart if you look at that. I don't know if that's some kind of a padding check or something like that. I'm not sure why they're as far apart there as they are. But point being, they are still both on the stack. But they can never write into each other with a shift, because what actually happens if you look at the assembly language code, you have to remember, stuff doesn't get operated on in memory. It gets operated on in a register. So what happens here is, in order to shift left X by 1, first the processor loads wherever X was, and it loads it into a register. So if you click on the registers window, again, if you don't have your register window open, you can go to debug windows, and then it's in here, registers. You can go into your registers, and you can look. EAX, right, is this value here, basically. It's called RAX, and well, I can also do all this. It looks like we haven't initialized our register window. You can right-click in here and get all the actual stuff you might want. There we go. RAX is basically the 64-bit version of EAX. So when I load this, it's going to load into the low part. EAX is the lower 32 bits of RAX. So I do that, and you can see I loaded in the value, right? What's going to happen now is I'm going to shift left the register. So you're not shifting left the memory location X. You're shifting left the register. So the register shifts up, right? And it went to 2, just like we would expect, right? You can actually do this in your watch window as well. You can type in RAX, the actual thing, or even EAX, I think, yeah. And you can see what EAX is. That's the low 32 bits of RAX, right? You can do that, and you can even do comma B if you want to, because this didn't work in the intro to C stream. The comma B didn't work because we were using an older version of Visual Studio, but now that we're using 2013, we can do comma B, which shows binary, which is really helpful, especially for teaching purposes. There's the binary, 64-bit register. And as we go through, you'll see it does the shift left, right? Now it writes the value that's in the register. It writes the low 32 bits of that register out to X. So the address of X, you'll see, still has 1 in it. It did not get shifted yet until we do this move to write the register value back. There it is, right? You see that there? So now the register value got written back to X. Now, and again, this is very unoptimized code. The optimizer would normally go to town on this, and it would just change it into a single shift and a write or something like that, right? But since this is unoptimized code, if you turn the optimizer off, it literally just outputs explicitly what you told it to do. And what you told it to do was to load X into a register, shift it left by 1, and then put it back out to the register. So now it's going to do the exact same thing again. Load back in the value, which it did, shift it, write it out. Load, shift, write, load, shift, write, load, shift, write. And basically what that does is that just keeps doing exactly that load, shift, write, keeps updating X, and so on and so forth. When you get to the end of X, when you get to the end of the 64 bits and shift it out the top, or in this case, when we get to the end of the 32 bits and shift it out the top, again, it's just going to take the 32 bits of the register and write them out. So there was no way to shift it into some other memory. This is in the register. The only thing that can happen is when you shift, I think there's like a carry flag that gets set in the processor that you could test. So you do know whether you shifted a 1 out, I think. There's basically a thing in here, if you look in registers, there's a flags thing down here, right? There's that gets set sometimes and stuff like that. But you can't access those flags from C. They're opaque to you. They're not actually exposed. So basically that's what happens. So that's why you can never write values into other values like that. The only time you would have an overwrite is if you were writing to a pointer and you wrote too many bits to the pointer, which you could do, right? You could have a pointer and write 64 bits out to it, but you were pointing at a 32-bit value, and then you would corrupt the thing next to that thing in memory, if that makes sense. Hopefully that clears that up a bit. Let's see. I don't think it had to do with uninitialized variable. Wouldn't that mean you would be doing a huge writing past into the buffer? I think it's because we did that. Is it possible to spill over? We'll use the same audio buffer to have overlay several sounds. Yes, we only need one output buffer, and we can mix all the sounds ourselves, which I'll show you how to do later on. Change hertz on A button pressed, the bug will resurface. No, that bug will not resurface. What you're seeing there is the fact that you cannot instantaneously change the hertz like that and expect to not have a sound clip. There's two reasons you will get that sound clip. One is that you are harshly changing the frequency right away, and that will cause an artifact. But the more serious artifact is you'll notice basically what we have here is the, well, you know what? This is going to be a long stream today anyway, I think, because we've got extra time. I'm just going to go ahead and show you because that's a very good question. That's a very good point that basically that you've brought up. And I think if we explore it, it may be educational. So let's go ahead and explore it. What the person writing in said is they wanted to change the pitch based on what the controller was doing, whether you push the A button, for example. So what he was saying is, for example, he wants to do if A button, right, then basically this tone hertz is going to change. It's going to change up to something else, like double that, let's say, 512 or something, right? So we're going to go in here and we're going to set that to 512. Does that make sense? I think this is what the person was saying. And so we kind of push that button. We do that, right? Why am I not hearing that? What did I do wrong? That is the A button, is it not? Did I type that properly? Tone hertz 512. Well, that was not as dramatic as I hoped it would be. I feel like that should have done it. Sound output tone hertz. Oh, well, duh. We have to recompute our period as well. So how do I want to do that? This is not a particularly good way to do that. I don't want to have to recompute all the dependent values every time. We should make that into a function or something. But let's do it again here. So I don't know if you could hear that. I'll run it one more time so that you can kind of hear it. When I push down the A button, you can hear the click that happens just on the changeover, right? And I assume that's what the person meant when they said that the bug resurfaces. But that's not a bug. I mean, it is a bug, but it's not a bug in our code that we wrote. It's a bug in this idea. This doesn't work. The reason that it doesn't work is because you have to remember, we recompute where we are in the sine wave every time. So if you look at how this works up here, basically what we're doing is we're using the running sample index and we're dividing by the wave period every time. That means our sound will only be continuous if wave period was continuous. If wave period suddenly changes to something else, we will have a sound glitch right at the point where it changed. So what you actually would want to do if you were trying to change the pitch continuously is instead of storing running sample index, you actually need to store where you are in the sine wave. You need to store T-sine basically up here in Win32 sound output. And then what you would do is instead of computing this value anew every time, basically you just add at the end something else to it. So basically we'd say sound output T-sine plus equals however far we want to go. And how far we want to go is basically one sample's worth, right? It's basically one sample's worth over that period. So that way, just the increment is now going to change by the wave period, right? That is what we would actually want to do if you wanted to avoid the glitch. So our code was totally correct. You were just doing something that is going to produce a glitch with the way that we chose to represent our sine wave. But the buffer code is still valid. And now we should be able to basically get something. Oh, whoops, we need to actually say sound output T-sine here because we are now outputting without that T. So we'll do that, right? There we go. And now we should be able to, did you hear that? No glitch anymore, right? And so I hope you guys understand what was happening there. I don't know if you do or not. Again, since it's a long stream, I feel like it can't hurt just to solidify that in your heads a little bit with a lovely one of these Microsoft Paint diagrams. I think everyone loves them. I think everyone knows they love them. So I'm going to go ahead and just put this out here. Okay, let's take a look. Here we go. So if you think about what was happening, we had a sine wave at a certain period. That is the worst sine wave probably anyone's ever seen, but this is Microsoft Paint. What do you want from me, people? What do you want? And so from peak to peak, right there, basically, that is the value that we're looking at. That is the period of the sine wave. And we had a period that we were saying was, wow, man, this is so bad. I really want to solve this. That's got to be something we do pretty soon. I got to get a better diagramming situation here. I got to get a better story. All right. Anyway, point being, we basically have, excuse me, we basically have a period here of our sine wave. And what we were doing before is we were just taking the absolute index. So basically we have a buffer, and the buffer is actually only this big, right? But we essentially were treating it as a giant linear buffer because running sample index, right? Running sample index was essentially incrementing ad infinitum. It's just getting bigger and bigger and bigger, right? And we were modding it by the buffer size to figure out where we were in the buffer size, but we were just using this value directly to compute where we were in the sine wave. So our position in the sine wave was also equal to running sample index, and we were just using the period as a divisor to map us into where we should be in the sine wave. What that essentially does is it means we are just direct mapping our sine wave into this buffer. It's a direct mapping, right? That just basically fills the sine wave as we go into our giant sort of virtual linear buffer, and we were just kind of mapping it circularly, right? So what happens if you were to suddenly change the divisor? Because there's a divisor here. We're dividing by the period of the sine, right, to do this. If you suddenly change that divisor, right, we were here in the sound wave, let's say. What you wanted to do, what you were trying to do is change the sine to a different period. Can I make, for the love of God, people, can we make a bigger eraser? Oh God, this is not a good drawing program. I need to figure out how to get a real drawing program in here. All right, anyway, what are you gonna do? So what you wanted to do was, what you were trying to do when you push that A button to make a nice continuous tone that doesn't have a skip, is you were trying to do this, right? You were trying to just at that point start oscillating more frequently. But what you actually did is you essentially because you just changed the period right out from under it, you can imagine there was basically two sine waves, one with one period, one with the other. You had the slow period sine wave, right? And then you had a fast period sine wave, right? And what you did instead of starting where you were and just changing the frequency of oscillation, which is what we wanted, you were taking wherever you were in the stream and jumping right to where this other sine wave would have been at that point if it had been the only sine wave that you were ever playing. That means you would discontinuously jump from here to here and then start oscillating, right? That causes the skip. That is the skip, because now you've got a discontinuity in your sine wave, and discontinuities sound like when you hear them. It's basically a very high frequency, because you have to imagine what that actually turns into is a very high frequency spike, one little tiny sine wave that moved you up to there, essentially. It's a very high frequency spike. So if you looked at it on a graphic equalizer, you'd be getting, here's your normal tone that you were trying to get, and there's this really high frequency spike here that just kind of quickly jumped in to make you move. And that's no good. So you don't want that. That's bad. Bad, 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 bad. So that's what was happening there. And that's why I said what you have to do is you have to track where you were in the sine wave, because then you can just accelerate that tracking, and you'll always know that you were starting from the same position. You can change the pitch all you want, basically. And we could go nuts with that, obviously, right? You could map the pitch if you wanted to. You could map the pitch to one of the sticks, right? You could say, oh, the pitch is something like the stick X or something, let's say, right? Or the stick Y. Let's do stick Y. So we could say, okay, the hertz is something like the stick Y divided by whatever the stick Y can possibly be. So that's 32,000 or something like this. It's 65536 divided by 2, but I'm just going to say stick divided by 30,000. So there's a change those to float, so that we do float math to get basically a value between -1 and 1 here, and we'll basically say that it's 512 is the tone hertz plus some value that more than that, so we can do 256 up or down times that, and then we'll cast it back to an integer. I think that's what it was. I don't remember what that actual value was. What was that value? Let's take a look at what we actually defined it to be. It was an integer, so we'll cast that back to integer. So we could do something like this, and this will actually allow us to go ahead and control it, I believe, with the stick. Let's take a look here if that actually works. Which stick did I do? I don't actually know. That didn't work. What am I doing? Oh, the A button has to be down. We don't actually want that. Let's just get rid of that A button check. I don't want to have to hold that down while I do the stick thing. Right? Makes sense? So the other thing that we might want to do now is we might want to get that latency down, because now we've actually attached something to the controller. And so what we probably want to do is when we fill that buffer, when we do the global fill buffer, we probably don't want to fill the sound buffer quite so far. So what we would want to do here is we'd want to introduce another variable that's basically saying where we would actually like to be relative to that play cursor. So basically what we can say is we can say basically our latency sample count, let's say, how many samples ahead of the play cursor we would like to be in general, right? And what we can do is we can introduce that value in a way that makes some sense to us. We can say that the sound output latency sample count is basically going to be equal to the samples per second, let's say, divided by 60. So 1/60th of a second is how far ahead we want to be, let's say. That might be a little aggressive. Let's do a 15th of a second. Eventually, we'd probably want that to be high, much higher, like a 60th of a second, so that we're constantly really good. But then we might get dropouts. So we're going to have to do a little more stuff when we actually get down to it and tighten the ratchet on the sound code. But let's do this now so that if you're running at 15 frames a second or higher, you wouldn't get any dropouts. So then when we go in here and we actually compute those values, what we'll actually do is say that the play cursor itself, the place that we're trying to write to is not going to be that play cursor. Instead, that value is going to be something else. It's going to, let's say, be the target cursor or something like that. And that target cursor is going to be the play cursor. We want to write to at least the play cursor plus however much the latency is going to be. So what did we say that was? That was sound. That's this here. That is the latency sample count. So basically, we're going to take wherever it's playing. We're going to say we want to be a 15th of a second ahead of wherever it's playing all the time. That's our goal. And then instead of play cursor, we're just going to change that to target cursor, right? We're just going to look at the target cursor and say that's what we're writing to, not the play cursor anymore. Make sense? Hopefully that makes some sense. And then what we do when we initially kick off our buffer is when we kick off our buffer, instead of writing the whole buffer, we will actually write the latency count times the bytes per sample again. We'll actually write that many bytes ahead so that we start off ahead as well, and we just try to stay ahead. So we're still getting a little... We're getting a little bit of a clip there. But you can see we're right on target now. So basically, I don't know if I introduced a bug by quickly doing that or not, but it could also be that that's just not enough ahead of the play cursor to make it actually work okay. I'm not sure which one that is. Let's make sure that this was sort of at least roughly correct, if that makes sense. Yeah, this is probably not the way to introduce that code, was to blitz it out like that, but I felt like we were kind of going in that direction, so we might as well. So let's double check here. Let's say that let's double check and make sure that if we just say that it's the latency sample count is the samples per second, we should be back to where we were before. So there you go. So I did introduce a bug, because basically that shouldn't change anything, right? Oh, duh. Yeah. I was even thinking this when I wrote it. One of the problems, again, I say this a lot on the stream, I think about things, but then my mind is occupied with explaining and it forgets the things it's supposed to do. In fact, we had that just yesterday with the unlock as well. Remember I said, we've got to unlock that buffer, and then I never remembered to unlock the buffer. So the problem here is the target cursor, when we do that thing, it could wrap around. So when we get to the end of the buffer, target cursor will be past the end of the buffer, and we actually need it to be back around. So basically all we need to do here is do that mod again. We need to make sure that we're always in range of the buffer when we actually ask to lock. That's it. I'm pretty sure that's the only thing. I was gonna say that this code should not be too hard to add in, and I don't think it is. So basically, we just need to do that. Move it out to where we think it's gonna be, map it back into the buffer, and then treat that like the play cursor. And now it should be correct. Oops, I've forgotten a semicolon there. All right. Yeah, and so now we can go ahead and go back and drop that latency back down to something aggressive like 15. And now we've got, not super low latency sound output, but it appears, like to me, for example, you can see. Right? So there you go. Now, we've got about, I figured this would be a 2-hour stream. We've still got 20 minutes. Let me cover a couple things. Well, I'll double check the thing for see if there's any questions here. Let's take a look here. Let's see. If we can live with a slightly less accurate sign, it can be approximated with polynomials. We don't actually need to do that. Well, I mean, we do actually kind of need to do that. You'll see. What we'll end up doing is we'll actually write something that generates the sign using the SSE2 instructions. We'll be totally fine. And we won't really be approximating it. We'll actually be computing it to floating point precision probably most of the time, although we could do a less accurate one as well. But because basically you have to remember, approximating something actually ends up being exact as far as the computer is concerned if you can do it out to the number of bits that are in the actual floating point value. Because yeah, that's not exact, but neither is the floating point value. The floating point value can never represent even pi, right? Pi is an infinitely repeating, it's got an infinite number of digits, right? It just keeps going. And so you can never accurately represent things in floating point. So we only have to, when we actually compute sine, we only have to compute it out to the number of points that the mantissa has in the first place, which is only like 24, I think. 24 bits. I don't know if that's actually true. That might be more than 24 bits. How many bits is the mantissa? Is it 24 bits? For some reason, I think it's 24 bits. But let's take a look. Floating point 32-bit mantissa. I think it's 24 bits. Let's take a look. Mantissa. Does it say what the spec should say? Here it is. Let's take a look. Internal representation. Okay, so it looks like it's actually 23. So it's not actually 24 bits. Oh, but it's 24 because of the implicit 1, I guess, is what they're saying. I don't know. So there you go. There you go. That's the table right there. And in double, you basically you get double that, right? Plus a little more than double that, because they assign less to the exponent proportionally. Anyway, yeah, not really important right now, but point being. Let's see. Okay. What about lead time between play cursor and byte to lock? Sorry, not sure I understand that question. Will the art and audio for the game be released into the public domain? No. Not for a while anyway. Do we get them for paying now while we are following along? Yes. All of the art, I mean, basically the game, you'll get access to the full game if you pre-order. So basically, you'll get all the art resources to play the game, because there'll actually be playable versions of the game released once we actually have it up and running, and those will come with the art. So if you're following along at home with the code, you will also be able to load the art from the game builds that ship, because people will start actually playing the game builds who don't even necessarily follow along with the code. And so yes, that art will come with that, but it will not be released into the public domain. If it does, it may eventually get released in the public domain, but it won't necessarily be coincident with the code being released. The code will definitely be released into the public domain, and it will be released presumably sooner if the art were to be later. So that's it. What is going on here? Okay. All right. Let's go back to the chat. Okay. Is it a good idea to use fixed point math for games that require deterministic simulation for multiplayer, or is it actually feasible to get consistent results with floating point math across different systems? It's a good question. There's people who've done it. I think Bungie actually did it that way. Basically what I would say is it is entirely possible to use floating point values to get determinism, because floating point is very rigorously defined, and most processors have to do it specifically in a particular way and all that. But there's a really huge problem that you run into, and that is the optimizer. Floating point operations won't come out to equal the same values if the optimizer rearranges the code. Because let's say, for example, and this is not very realistic, but I'm just giving you a very trivial example. Let's say that I have a couple values and a couple operations between them. Obviously, math can be rearranged in different ways. I can do a divide first, I can do a divide second, that sort of thing. Depending on what's happening on the platform, you may end up in a circumstance where you get different orders of operations happening, which produce different results because of rounding. The floating point values have to get rounded, obviously, because when you do floating point math, you end up with a number that's more precise than you can shove back into the 32 bits. So you basically have to round that last bit one way or the other. And so if you do the operations to opposite order, you can get different things. There's also a thing called operator fusion, which is when, like, let's say one platform has a multiply add, so a single instruction that does a multiply and an add together, and then another platform doesn't. Well, a platform that has a single multiply add could do it at higher precision than one that has to do a multiply, round, then add, right? Because it has to store the value back, it's got to do that round, so it'll do multiply, round, add, round, instead of multiply, add, round. And that's a problem too. So this is a huge problem. So could fixed point be an answer to that? It could. I don't know. I mean, it depends how you want to set up your multiplayer architecture. I am not an expert at such things. I think different people would have different arguments about how you should and shouldn't go about structuring code that way. But it's something to be aware of, certainly. It's a good question, and it does have ramifications, is really the answer I can give you. And different people choose to attack that problem different ways. You sometimes use bool and sometimes use bool 32. Mostly that was because I was on the stream. Really, I don't ever want bool. So basically, we can actually go in here and just replace. We can just replace bool with bool 32. I don't ever really want bool. I don't ever use bool in my own code. I was doing that for a while because of the stream, but I never actually do that in real life. So we can just get rid of that entirely. You'll never see me type a bool again unless I forget again that I'm supposed to be doing code my way now, not like the intro to C stream. Let's see. There is a red volume slider right on the OBS main window. Okay, cool. I will go investigate that after we're done. Thank you. Let's see. Are you going to use ETW to log context switches for the game? That is a funny joke. No, because it's insane. It's such an awful API. Is this the audio API we'll be using in the final version of the game? Yes. Direct Sound is perfectly usable to ship games. It's pretty reliable and it runs on just everything. You can run on Windows XP, it'll work. So we probably will ship the game on this. We don't really need anything else, I don't think. Given Direct Sound is actually COM interfaces, is it a safe thing to call into the interfaces without going through the COM layer, and especially without even initializing COM? Yes. It's the Direct Sound create call does the initialization for you. Try paint.net for drawing. Okay, I will. Let's see. Target cursor doesn't wrap the buffer size. Yes, whoever, Caboose 2311, you were right on target there. Let's see. I think that's everything. Can we do an episode on Emacs editing techniques? Yes, we will do that. That's already on my list. We will absolutely do that. All right, we've got 10 minutes left now, so I am going to go ahead and talk about basically, let's see here, one more thing, two more things. Yeah, so no, we've got 3 more things that I want to talk about on the stream real quick. Just real quick. Really simple stuff. Should not take any time at all. We've got 10 minutes left, so I'm just going to go ahead and cover those. So we'll get them in here, and I can cross them off my list of things to talk about. So apparently, our our X input stuff, there's even another library people were saying was sometimes the only one that was on their machine. Basically, it was called X input. What is it? 1.4. I don't even remember. Let's go ahead and check this. This is ridiculous. You'll see why it's ridiculous in a second. X input library versions. Let's see if we can get a thing here. All right. So there's X input 1.4. There's X input 1.3, and there's also X input 9.1.0. I am not kidding you, ladies and gentlemen. Those are the versions of X input that they shipped. That is the way Windows goes nowadays. It's absolutely ridiculous. But that is how it works. And basically, some people said that only that one was available sometimes on certain machines. And so what we'd like to do here is just further explode our set of checks and basically say, well, okay, excuse me, let's try and load that one as well. Now, I'm not sure what the actual file name of that is, so I'm going to attempt to look for it and see which one. I don't know if it's on this machine. Let's go ahead and go over here to Windows again and just do, again, that dir/s x input star. Let's just see what versions there are. So it's on this machine. We've got this one, x input 9.1. So let's go ahead and see if we can load that one as well. And that way we've just covered absolutely all our bases, no matter what Microsoft decided to poop out into their Windows operating system. We will hopefully have coverage there. So let's take a look at that and double check that that works and that the controller still works if we load that library, because I've never actually tried loading that library before. Let's take a look. Load that library, and it got loaded. And the controller works a-okay. All right, so we're good there. No issues with that. So that's one thing off the list. Not much, again, nothing to talk about there. Just had to make sure we covered all the bases. Last thing I want to do is talk about the dead zone. I realized I did something stupid. This would not have been a problem when we actually went to handle this stuff for real. But the joke code I typed in here was already dumb. And I didn't want to leave it in there without an explanation of why it was dumb, just in case people internalized it and didn't think about the dumbness. Basically what I did is I shifted this down because I was just like, oh, I want to kill the low, I want to make it a very low value so that when you push to the side, it's not scrolling by infinitely fast. Because This is a 16-bit value, so it'll go between 32,000, negative 32,000, something like that. And we're scrolling in pixels when we do our X offset. So that's way too many. I mean, our whole window is only going to be like 1920 pixels wide at best. And we were right now using just only 1280 by 720. So scrolling by 32,000 would wrap the screen tons of times in one scroll. So I was trying to scroll that down. Now the problem is this is perfectly valid. Shifting down by 12, that's basically the same as dividing by 2 to the 12th, right? But there is a catch. The catch occurs when there is a negative number. By default, when you shift in C, I believe it does sine extension. And what that means is if the number was negative, so if that high bit was set and you shift it down, it continues to shift in the high bit. That leaves the number negative if it was negative before. Now, I want to just show you what that means because I realize it's a little complicated to understand. But we come in here, first time through, right, and we take a look at what goes on. We have an X offset and a Y offset, and you can see, excuse me, man, the coughing, it never stops, of zeros, and we are going to add to those zeros how much we want to offset by. Now stick offset, I'm sorry, X offset and Y offset are both 0, like I said. So what we would expect to have happen here, right, is we would expect to see 2035 shifted down by 12, which is 0, right? So because that's basically there's what's called a dead zone on the controller. The controller is basically kind of noisy. The inputs aren't perfect. And when the controller is back at 0, it may not be right at 0. It may be anything from like negative 4,000 to positive 4,000 or something. There's like a huge range of what centered might be in the controller. So basically, that shift by 12 should have totally killed that noise because the two values that are on the controller, you notice, are both 0, right? But when we actually go to compute these lines, you'll notice that's not what we get. We get negative 1 and 0, right? Which is what causes that persistent scroll. I was just saying, oh, this controller is broken because I thought the controller was broken. That's not the case. That was just me being dumb. Basically, what's happening here, if you look, is if we see what actually happens when we do this shift, right here, right? If we look at what actually happens there, we will see the problem. The problem is that value, when it gets shifted, where's my debugger? Where is my debugger? There it is. That value, when it gets shifted, this is a binary value, right? If we look at the binary value, that's a 2's complement value. The high bit is set. That means it is negative. What's going to happen when it shifts it is it's going to shift in the sine bit. The reason it has to shift in the sine bit, that high bit, that's going to be 1 anytime the number is negative, is because if it shifted in a 0, the number would flip from negative to positive, right? So what it does is it shifts in a negative, it shifts in that one, the negative to keep the number remaining negative, and that's just 2's complement, which we didn't really cover too much, but that's what's going to actually happen. When that happens, you will notice that we basically end up producing a value that's all 1. You know, when we shift it down, it's going to be all 1s, because we shifted it down enough to knock out, we shifted down 12 places, right? And this thing is only 16 bits long. So basically we ended up with just these 1s that were here, and we shifted in 1s for the rest. So these 1s are those 1s, right? They went down there. And we shifted in a 1 for everything else. No matter how far down we shift the negative value, it'll never go to 0. It only goes to negative 1. So it's not really the same as an integer divide at that point. That is a crucial thing to remember. And I didn't even think about it, and I just kind of crapped that in there. That was a bad idea. So that's not good. What we actually wanted to do is we actually wanted to use a real divide here. We actually wanted to use something that was basically, 2 to the 12th, let's say, something like that. And that's going to be, 256 with 4 more extra places. So 256, 5, 12, 10, 40, 20, 48. So it's going to be something like 2048, let's say, right? We're going to do that divide, something like that. Maybe, not sure what we actually want it to be. Maybe we want it 4096. I think it's 4096 because there's actually 1 extra shift. So this is actually a little more. But but that's still a totally fine value. And I can feel that that's not quite all the dead zone. You see how it's got still a little bit sometimes of a bit that's happening there? So I think the dead zone is probably somewhere around 4096. And I think if we actually look, so I'm gonna stick with the higher number. Oops, that's the wrong editor. Tell immediately when you type into it. 4096, 4096, and that should handle the dead zone properly, I suspect. All right, looks good. The only thing I wanted to check as well is whether or not what the X input definition for the dead zone was. Because if I remember correctly, they say what the dead zone is in here. And like I said, we're going to handle the dead zone properly. This is not proper handling of the dead zone at all. We're going to handle the dead zone in later editions more properly than this. But you can see actually the left and right have much higher dead zones, actually even than 4096. Those are really high there. So technically, actually, we would want to kill any number that was above those. So keep that in mind. We'll deal with that actually a little bit later. Okay. So basically, that's just something to keep in mind. In fact, you know what? I'll go ahead and put a to-do in there so people can see it and know that it's okay. And we're going to get to that later. Note or to-do, Casey. We will do dead zone handling later using X input gamepad, and there we go. All right. So basically, we will actually do that later. You'll see that happen later on, and when we actually process this joystick to shove it into our actual game properly. All right, so that's the dead zone thing. And then the final thing was just one bit of cleanup, which was that def window proc technically should have been def window proc A. Again, this is just cleaning up things that, for people who want to compile in Unicode, anytime you see one that I've missed, we're just trying to make it so that if anyone does compile it in Unicode mode, nothing breaks, basically. So there we go. All good. I think we have come to the end of the stream. I don't think we've got anything else. It looks like that's the end of the questions too. So thank you everyone for joining us for this special 2-hour holiday, Thanksgiving holiday episode of Handmade Hero. I am delighted to see that so many people actually joined us. I was figuring today would be not many people on the stream because of the Thanksgiving holiday, but it looks like we still got quite a few people. So thank you so much for coming and hanging out with us while we got our sound code working, and we did some other kind of fun stuff as well, talked about floating point and all kinds of other good stuff. If you would like, again, to pre-order the game, you can get the full source code here, and that will come with art assets as well, like we talked about on the stream. If you want that, you can pre-order it here. If you want to email a question, you can email it here. We're still working on the forum, so hopefully that'll soon be a forums button. You can actually go and talk to other members of the community as well. Again, the Twitter stream, I usually post when the things are going to be as well, so that you can get updates on when the next stream is going to be, and of course the YouTube video archive. So go to handmadehero.org if you need anything. We've tried to put most of the stuff there that you need, and the forums will be coming soon, which will have even more stuff, so that should be good. Thank you everyone for joining us. Tomorrow will be 11 a.m. again. Then Monday we'll be going back to 8 p.m., so we'll be back on regular hours. Fridays will probably always be sometime in the morning, though, so the people in Europe can join in. So Fridays will be early in the mornings from now on, basically. But Monday through Thursday we'll be back at 8 p.m. For next week. Thank you, everyone, for joining us. It was great to see you, and I hope to see you again tomorrow. Have a happy Thanksgiving for those of you who celebrate it, and for those of you who don't, just have a good rest of your day.